So when we work with FC is equal to FG, we can expand it because we know FC is really equal to M times AC, and FG can be equal to a lot of different things. So we are going to I'll show you how you can derive different formulas with this. When you are doing your assignment, I would encourage you to do this manipulation of formulas and not just look back at our notes, because on a test, you won't just get to look back at your summarized formula, right? So you should get into the habit of knowing how to practice and work with it. So anyways, here we go. So let's say we take FC is equal to FG. So I can say FC is M1 times AC is equal to M1 times G. M1 is the same on both. AC I can expand into V squared over R. So this is one formula. If you're just dealing with M1 and not your big plan. Generally, you won't use this one too much. You'll only use it if you know the gravitational field strength. Okay? Or another one, FC is equal to FG. I'll go M1 times AC again. Instead of FG just equaling M times G, I'm going to use my planetary big G times M1 times M2 over R squared. So again, I can cross out M1 on both sides because they're on both sides of the equal sign. And realistically, it doesn't matter what M1 is, because we just talked about that, right? Theoretically, it doesn't matter what M1 is. It doesn't matter if it's a huge space station or a small one. It's going to be the same. So it's really irrelevant, and that you can see that quite clearly in the math in this section. Okay, so anyways, let's expand AC to B squared over R again. Now I have G times M2 over R squared. Now I'm going to cross multiply my fractions. So now I have V squared times by R squared is equal to G times M2 times by R. Well, there's R squared here, which is like R times R, and one R here, so I can cross those off. And then just to kind of simplify things, we're going to say V squared is equal to G times M2 over R. So you can work with this formula. You can, if you're solving for V, then you would square root each side. If you were solving for M2, you would rearrange to solve for M2. If you're solving for R, you rearrange to solve for R. So this is just one example of how to work with our two formulas. One more. FC is equal to FG, where M1 times AC is equal to G times M1 times M2 over R squared. Again, M1 is irrelevant. This time I'm going to use my different AC formula, my 4 pi squared times by R divided by T squared. Because if I'm given information about my period and not about the speed, then I would need to use this formula for AC. This is equal to G times M2 divided by R squared. Okay, again, we'll cross multiply. So I have 4 pi squared times by R cubed, because I have R times by R squared. So now I have R cubed on that side, is equal to G times M2 times T squared. So again, you'll be able to, depending on what you need to solve for, you then will rearrange that formula to solve for T or to solve for M2. But let's look at this one a little bit more closely in light of what we learned yesterday with Kepler's law. So this really, Kepler's third law said that R3 is proportional to t squared. That's what Kepler's third law was. Well, Newton's mathematical formula here has both R3 is proportional to t squared. So this is, we can say that Newton's laws, this stuff is based off of Kepler's third law. If it's like he just said that they.
No, I know, but like the sign. Is it a certain way that it means it's proportional and the other way means it's not?
Oh no, this just always means proportional. The only other kind of relationship we talked about was inversely proportional, and that would be like if there was a 1 over this, that would be inversely proportional. Yeah.
What does it mean for something to be proportional?
That if one increases, the other will also increase. Inversely proportional would be if one increases, the other decreases. Yeah. So, good question. Let's think about this logically. Let's think about, say, the moon, a moon orbiting a planet. The farther it gets away from the planet, so the more that distance increases, the longer it will take to go all the way around it, right? We needed like a solar system model kit or something here, don't we? Like, so if a moon is really close, it's going to go around and around in not very much time. But say now the moon is way out here. It's going to take that much longer to do one whole revolution around the planet because it's farther away. So it makes sense. The farther away something is from whatever it's orbiting, the longer it's going to take to do one full orbit. So we can then say they're directly proportional. One increases, so does the other. Yes? Okay. All right, so now here's the specifics about what each of these are. We're familiar with all of these. The only thing with these questions is that make sure your units are always the same. So, oh, and it doesn't even say this here, but T is in seconds. So if it's asking for time in hours, when you're doing the calculation is with seconds. So your answer for T is going to be hours. So let's actually look back here for a second. That's all the way back here. And this, we said, this is called the period, right? Yeah. So, and period is the time it takes to do one revolution. Time it takes to do one revolution. So let's say, it asks you something and it tells you that it takes 7.5 seconds, or, never mind. I'll just tell you when we get to a question. But just remember, it's the time per one revolution, and it's in seconds. So just make sure you're being really careful about your conversions for these types of questions, because there's a lot of conversions sometimes, and they get you. They got me a couple times, so.